So good morning to all. Welcome to CSCS for this visualization tutorial. I'm on tape, so I need to speak and I can't repeat the same thing 3 times, etc. And then we'll do some editing of the video so that you can play it back later. This is the first day. We're going to be here for 2 days. And as I advertised it on the web, we're going to spend a lot of time with Python. We're not going to program much in Python, but we're going to access data via the Python interface and see how it fits into the environment of the visualization softwares. Here's what we're going to do. Take a very quick look at Matplotlib, very quick because really we don't have much time. We want to put our emphasis on 3D data. Matplotlib is a wonderful package for 2D plotting. It's the de facto standard of 2D plotting, if I may say. And we'll see how NumPy arrays can be plotted in Matplotlib. Now, here's the first keyword, NumPy. Is this a foreign word to most of you, or do you have a minimum of experience with NumPy? Who doesn't have any experience? Who has never heard of NumPy? Just a few of them. Good. We're going to learn just the basic. In order to not be boring for the other people, I included really the minimum, but the minimum that we need. We'll take this very quick look. We'll see how the ParaView, so ParaView is one of the 2 softwares we're going to use. ParaView is a highly successful parallel, that's in the name, but we don't have to use parallelism. By default, it's a normal standalone serial application, but it has the power to connect to a parallel server. We're going to use the Python shell that is embedded into ParaView to do the very first data manipulation. Then we're going to talk about a data visualization pipeline. That's the standard name. And we're going to talk a lot about VTK. What is VTK? VTK is a C++ toolkit. We're not going to do any C++ programming, which is great because, you know, programming with a language like C++, you have to compile, test, edit, compile, test, etc. It's a very long thing. Python instead is an environment where you just try things. It's an interactive prototyping environment, so that makes it really easy to test things. VTK is a C++ toolkit, however, it has a Python wrapping around it. So any C++ class can become a Python object, and then we'll learn how to get what is important for us for visualization, get the methods useful for our treatment. And then we're going to tie together the NumPy arrays and the VTK object. You probably don't have the same long-time expertise that I have with VTK. VTK exists as of 1988, I believe, was the first publication as a toolkit. Programming and accessing the data arrays in a VTK pipeline is kind of cumbersome. It's complicated. There's a very rich API, and you'll have to take a book that is that thick to learn every possible ways to get your data into the right format. So that's a little bit unfortunate, and this is why I'm not interested in teaching the C++ aspect of it. NumPy, however, is very flexible. You'll see through our examples, it's very straightforward. It's very natural. So the idea and really the emphasis of this course is to be able to plug in directly the NumPy arrays into the VTK objects. And if we manage to do this, you can forget about all the last 20 years of VTK programming, which I have done, but really it's cumbersome to address directly the VTK object. We're going to write full pipelines in VTK using the wrapper. So VTK is a library, and then VTKpython is the executable, which brings in all the Python environment for this library. And by writing a full pipeline, what does it mean? To do visualization, we need to read the data, transform the data in some ways, and then we need to display the data. So we need to make a graphical object out of that data. All this succession of things is called the pipeline. And here, again, I don't have very much time at disposal. I will not be able to explain every little detail, every little line of things. We're going to show you the skeleton, the minimum skeleton of Python object necessary to get an image on the screen. Everything else, making the colors pretty, making the labels, is left as an exercise for you at home later on. And by the way, if you are a user of CSCS, if after this class you run into problem, you have something you don't manage to do, you can write a help request at CSCS, and I will be delighted to help you do the fully elaborate pipeline. Okay? So in this class, because we have a large number of people and we have many things to do, we're going to look really at skeletons, at things that are the bare minimum to get things working. We'll then do, so there, I just explained that there's quite a lot of details which you learn by experience. And by the way, the web is full of examples. So if you don't know how to set up a color table for a VTK array, you just Google for it, and it will find an example. And I'll show you where exactly those examples are. ParaView is a turnkey system, so to speak. In ParaView, the color table will already be there, etc. The surface will be colored and rendered in a good way right from the beginning. So it takes away some of the burden of the details of the pipeline. In the early part here, we're going to talk about the essential, most common data types, which are all grid-based, so the rectilinear grid, the structured grid, the image data. And then here we'll talk about some more elaborate data types, which ParaView and Visit support. And then this afternoon, I'm hoping we'll be there this afternoon, we'll talk about the Python Programmable Source. This is where we will learn how to bring into ParaView data that comes from your own simulation, presumably, hopefully, using NumPy and all those nice Python packages. So if there are experts in the room here in Python, you're going to have a good time, because you're going to see how the power of Python to read your data, do maybe some preliminary analysis, will be able to be imported into the ParaView environment. There's the source, there's the filter, and then there's the calculator. The Python calculator is completely NumPy based. So anything you know in NumPy, you'll be able to apply and see the result in ParaView. Finally, we'll learn how to connect ParaView, a client, to a remote server. Now, the remote server can also be on your own laptop. ParaView is made of multiple application programs. The first one is called ParaView. The second one is called PV Server, so it's the server part. And when you run ParaView at the terminal, it actually runs both processes together, and it's transparent to you. But the first exercise is actually that you can do is actually run a server on one terminal, run a client on the other terminal, and have them connect to each other. This is the first part, and then once we know how to do this, we connect to a remote server, which in our case will be the supercomputer. That's it for the day. Actually, it's going to be a lot of things, so bear with me. Resources, I've talked about it. So PythDaint is our supercomputer. We're going to use in some cases, we're going to use a VNC server running on the graphics node. So I have a script to do the job allocation, and we'll see about this. And then there will be your laptop. Software, this is what we'll use. So NumPy, VTKpython, which is the wrapper to the C++ library. The plain Python interpreter, which works just as well. IPython if you have it. It's not obligatory, but it has some added features. PVPython, maybe, if we have time. PVPython is the Python. If you want, it's the identical piece. Here we have VTKpython. PVPython is the Python driver for ParaView. And then the final one is PVBatch. We will learn, I think tomorrow morning, how to submit a job to the supercomputer running a Python script, which we have elaborated together, and it will run by itself without the need to open a graphics window. And it will be GPU accelerated, so you'll have the full speed of the GPU, and you'll have your images, your movie, whatever, created automatically. This will be done with PVBatch. PVBatch can run in parallel, so we will see that. VTKpython can also run in parallel, but I don't want to make it too complicated. We have a lot of things to do already. So we're going to concentrate on a single CPU run when we execute VTK pipelines. Accounts. You all have an account. It expires tomorrow evening, more or less, so don't keep any. If you've made up some fancy script, don't forget to copy it to your USB key or mail it to yourself or whatever at the end of the day tomorrow, because it will probably disappear. I recommend passwordless SSH to Ella. Okay, Ella is the server where your home directory will be. Windows user, by the way, into my presentation. It's time to tell you where the presentation is. However, we need access to the computer. So that's the first thing to do. You need to SSH with your course account. That's the first step. I stop talking until you have done. And then I will add the path to Yes. 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 It's the same home. It's the same home. Yeah. Oh, what I mean, it's the same file system. So the tutorial notes are in my directory /users/gfab/project/ParaView tutorial 2015 PDF. If you are on Castor, you see that. It will be, you have to use the course account to access Daint, but the principle will be the same. So if it works for Castor, it had to work very similarly. So yeah, for the moment, don't worry about this. So doing an SSH to ELA is really, ELA is the name of the server here, is really the first thing you have to make it work, using the password that was given to you. You can try things, and I need to keep going because of time running. So Matplotlib, I have prepared here a particular directory with some introduction exercise. The exercises are already made. The idea is to learn by example. There's exercise 1, 2, 3, 4, 5, all the way to 10. Once we have a VNC desktop allocated, you will be able to do this. And the idea is to run Python at a terminal window and to execute those files. I didn't want to make this an exercise for everybody because I'm pretty sure at least half of the room here has already some experience with Matplotlib. So I leave this as an introduction, which you also find in this wonderful website, the SciPy lectures on the web. This is the address of the lectures. And some of the examples I've taken are also from the same website for NumPy. So let's talk about this VTK NumPy integration. What's the big deal? ParaView, and tomorrow we will also talk about Visit because it has some complementary features which are really quite nice. They both use the VTK C++ library. On the other hand, in a parallel world, if you want, Python has really flourished over the last 10 years. There's a lot of scientific packages available in Python, and you'd like to bridge the gap between those two worlds. This is the idea of the VTK NumPy integration, is making a transparent exchange of NumPy arrays in VTK. And by the way, because both ParaView and Visit run in parallel, all of the things we do with NumPy will also eventually run in parallel with an MPI-based environment. But that's really an advanced topic for the VTK objects. What are they? They're the fundamental structures in VTK. They represent scientific data. Scientific data is most often in the type of simulations we run here is grid-based. You can also have particle-based data. It's completely possible. And if I insist on the word mesh, and if you think in your head, oh, I have an SPH code, I don't have a mesh, it's okay. An SPH code is made of points, and the points are also a VTK object. So it's completely fine to come with data that is not based on a structured mesh. And I said structured, but we also have finite element meshes. So it's really a first-class citizen in the VTK object. And then we'll have variation, so multi-blocks, adaptive mesh refinement, trees, graphs, tables, all of those are VTK objects. In general, the data is stored at the points or at the cell centers. In fact, I'll come right away to a limitation of VTK, which comes up every now and then. People who have face-centered data, they cannot directly use the VTK toolkit. We will concentrate on point or cells. And the data can be scalar, vector field, tensor field. It can be really quite a variety of things. The finite elements can be what we call the zoo of elements. So anything from the tetrahedra, anything from the linear elements to the bilinear elements, etc. Tetrahedra, hexahedra, and so forth. Now, the NumPy arrays. NumPys, for the really beginners in the room, NumPy is an n-dimensional array with an efficient memory storage, such that we can process the data very efficiently. The absolute best resource I have found are the Cyber lectures, which you will find at this address. In all of the exercise and all my demonstrations, we will use NumPy in one of the standard way of using it. At the Python prompt, we will import NumPy as NP, which means anything else after the import statement will be prefixed by the NP name here. And this is enough to declare an array called A of 4 elements, 0, 1, 2, 3. There. That's almost all the NumPy expertise you will need for this class. Okay? I'm not going to be difficult with you. Here's a particular method here, a range. 10 goes from 0 to 9, and here automatically we'll have an array of 10 numbers. Not difficult. And then something we're going to use, so be a little bit careful here. Once we have an array, such as A, we can index that particular array with 3 numbers, a start index, an end index, and a step. So if I start at index number 2, I am here, 0, 1, 2. If I go to index number 9, it would be to the end. And if I skip, this is the step. If I take 1 every 3 elements, I will go from 2 to 5 and to 8. And that's my answer. Okay. Now this indexing we're going to use when we'll talk about distributing data among multiple processes. If we have an array, a NumPy array, and if we want to do distributed computing or parallel computing, we'll want to take this piece of the array, give it to this processor, then the next piece, and the next piece, and so forth. I think you got the picture. And we're going to use exactly this syntax here. Okay? All right. I think that's all the NumPy we need to know to continue. Actually, there's a little bit more. Here's an example with where each of the elements are not a single scalar field, but it's a tuple with 3 numbers. Why did I choose 3 numbers? Because it's typical of a vector field. For example, in fluid dynamics, you have a velocity field with the u, v, w components of your velocity in 3D. So this would be, okay, here I call it momentum. Same thing. I have an array with 4 different tuples. The shape of this array is 4, and it has the size of the tuple is 3. And then a couple of things which will be very useful for us. This particular notation, if I take all with the double points here, this means take all the array elements and only take the 0th index. So that's the first index. If we do this, we're going to take 0, 3, 6, and 9. If instead we say take the first index, the index number 1, it will be 1, 4, 7, and 10, and so forth. Okay? Now we're also going to use this quite a bit, so make sure you understand this really basic syntax of the NumPy library. One more thing. In VTK, okay, often we talk about 2D or 3D mesh. So that's the topological dimension of the mesh. It's 3D. But the data, so let's say we have a mesh of 10 by 10 by 10 in each of the axes, ijk. How do we store the data? The data are actually stored as a VTK object in one straight linear array. So this is actually exactly the form that we will use. It's a concatenation of data values, a straight line. And this can be made to represent a 3-dimensional grid of size. Well, because we have 4 elements, this can only be a 2D array, and it's a 2 by 2 array. So this could work as the momentum vector field for a 2 by 2 mesh. And in fact, I think that's exactly the exercise. And this is the morale of the whole day. If we are able to take a NumPy array and visualize this in ParaView as a 2 by 2 mesh, and you see here I have 0, 1, 2, 3, 4, 5, 6, 7, 8. Here, my tuples have been placed in the right position on the mesh. If we are able to do this, I'm satisfied with your understanding of the tutorial. And then, by the way, for some of you more expert, more advanced user of NumPy, we'll be able to use something like this, for example. From the NumPy package, take the linear algebra method norm, which does a normalization of the vector, and apply this in ParaView to your data. You have to think that if I had been teaching this class 2 years ago, I didn't have a normalization button or filter in ParaView. It didn't exist. I had to program it as a loop for each vector element, calculate square root of a plus b plus c square, etc., divide, etc., etc. A big mess. Today, and this is really the first year I teach this like in this particular way, because it's the first year as of ParaView version 4.3 that we have this tight integration between the two toolkits. Today, I can just take NumPy linear algebra norm vector, bam, it's one line, and I'm done with it. So we'll learn how to do this inside the Python calculator. All right. I think I've motivated this quite a bit already. And probably somebody is going to say, let's take the example of a gradient. There already is a gradient. Just like there is a norm, there's a gradient in NumPy. Why can't I use it? Well, the NumPy gradient does not know the concept of an unstructured grid. So that's the real advantage. The real advantage now is that we are tying together NumPy and also the knowledge of the underlying grid to do our computation. So I will be able to, with a sub-package from the VTK and NumPy interface called algorithms, I will be able to use the gradient from the algorithm package. And I'll answer that particular question. All right. Any question before I continue? NumPy arrays, okay, a very efficient way of storing numerical data with a very few methods we'll use. For example, the shape, the indexing, the sub-indexing like this, and that's about all we're going to use for the demonstrations. Now, let's talk about the pipeline. What is the pipeline? A couple of years ago, there was a great article by my colleague Ken in the transactions called, the article was called, I don't know, visualization pipeline, something like this. Anyway, I copied a couple of pictures, and this is a screenshot actually from the paper. A visualization pipeline is a data flow network, which means we read data, we process data with, and each of those are modules, and then eventually we make an image. And we often talk about this as sources, the source of the data, the filters, and the sink. The rendering is a sink because we make an image, we save it to disk, and then that's it. The data is no further processed. So that's why we call this a sink. This is a pipeline, and we're going to see this visual representation of the pipeline inside the ParaView graphical user interface. That's an advantage. If we program VTK with only the Python interface, we're not going to have this visual representation here, but it will be programmatically, we'll declare one object, then another one, and then we will attach those arrows here. It means that there is a connection between the modules. We will attach the modules together. We'll see the syntax about that. One more thing. Each of those modules can have 0 or more inputs and 0 or more outputs. So of course, a source does not have anything above, so it has 0 inputs. A sink has 0 outputs. And here we can have actually multiple inputs, for example. So we can have, here I have a linear tree. Well, yes, a single branch. I can have multiple branches in my pipeline. What about the execution? Execution can be event-driven or domain-driven. What does that mean? It means that I can modify a particular parameter of this isosurface module, and oftentimes those are the questions from beginners which we see on the mailing list. People say, I've modified this, but nothing happens. My picture didn't change. Why? Where's the bug? There's no bug. The reason is in VTK, the render here decides when to execute things. You have to imagine that we're doing large computation, big data. If I have a terabyte of data here, I don't want to re-execute this full pipeline every time I touch one little piece of my pipeline. I would prefer to change multiple parameters of my pipeline, accumulate all those changes, and then say, okay, now I'm ready to execute, and the data flows through the pipeline. So that's the reason for this being the render, the trigger of the execution. How does it work? It works in multiple passes. You build a pipeline, and each of those modules must declare what is the region of space they're capable of treating. What does that mean? If I have a source here, I give it a file name, I read, actually, I don't want to say the word read. I look into the file, and I see that there's a mesh that's 1024 cube. It's there. Okay, that's the first pass. It's to discover what is in the source. And I advertise this. This information goes through, you see, in this particular direction, through all the pipeline, such that at the end, the sink, without having read any data yet, the pipeline knows that there will be a mesh of 1024 cube being visualized. That's the first thing to do. Second pass, the application decides which region should be processed. If I'm running with a single processor, the decision is very quickly done. I say, I'm alone, send me the whole data. There's no other way to do it, unless I'm doing something called streaming. Streaming, if the data is really so big that I cannot process it with the memory I have on my computer, I could say, I will process it a little bit at a time. So give me one chunk, then a second chunk, then and so forth. This is streaming. It's more advanced. I have an exercise ready to demonstrate that. We will show that. Finally, when we have decided who does what, the pipeline can execute. So we read the data, and then we process it. So you have to keep this idea in mind. I'll go forward. In Parallelism, this pipeline will be replicated everywhere. And of course, at that time, processor 0 will say, give me only 1/n part of the domain. So if I have n processors, each one of them will do a smaller part. And then we will merge together the image. So the pipeline. In ParaView, this is the image we will have. So we will see the file name here, multicom. That's the very top of the pipeline. Here's an isosurface contour. And then here's a branch. You see, we can do a histogram. We can do edges. We can have multiple sources, etc. This is our pipeline browser. This is what we'll see in ParaView. And it's basically the same thing. We have, it doesn't show which one is a source, which one is a filter, but it's pretty obvious. What we don't see are actually those two things here. In ParaView, the mapper, which transforms the information into a graphical object, and then the rendering of the object is done automatically. Okay? So that's the advantage of that. The syntax is exactly what I just said. In ParaView, this is Python. So create an object, time source. There's a macro called show, and you're done. And it will show up on the screen. We'll do this exercise. Actually, yes, let me finish. In VTK, it's already a little bit more complicated. We'll have a source of data. This is an image data. We'll have a geometry filter. This is really the filter. And here again, here already, we set the input of the object geometry to be the ID. So there, the missing arrow is actually right here. You see, you program it just like you think about your pipeline. The pipeline that I have here, you have to imagine those arrows, those green arrows are right there connecting my object. Set input there. Then there's the mapper. And here I have a little bit of a different syntax, set input connection. And here I have set input data. I will explain why there's a difference. But you can see that the geometry output is the input of the polydata mapper. So filters, sources. In ParaView, we can see examples here through this screenshot. Under the sources, we have all those different sources. And the very last one is the one I use all the time to give demonstrations, to make sure things work. So the little cube with 8 colors, which I showed you 20 minutes ago, that was exactly this, the wavelet. It's a 3D image data grid. Filters, there are multiple categories of filters, as you can see. And here is my contour and my slice, etc., etc. Finally, I said that the VTK pipeline is triggered by the rendering part. So it's the very last part here, rendering, and this is why I have an up arrow. The rendering decides to make an image, and we program it like this. We get a VTK renderer, a VTK render window. We add the renderer to the window, and this command here, you will be repeating multiple times through the exercise to actually make the image. There. Streaming, I've briefly mentioned it earlier. If we can break the data into multiple pieces, we can actually execute that in multiple passes. This is called data streaming. Let's see now the full pipeline. Here's the source of the data. Here's the geometry filter. Here's the mapper. We have to make a graphics object, and this is called an actor in VTK. So we define it as an actor. We set the mapper of this particular actor to be M. So there again is my pipeline. We go to the top of the screen, we define the renderer, we add the window, and then we trigger the execution here, and we start the interactive thing. Now don't worry, you don't have to remember this and copy this. It's all there on the disk for you to execute as your very first exercise will be to take this, make it run, prove to yourself that, hey, yeah, it works, this is the pipeline. And then we'll modify just a few things. Now, there is a difference in syntax. There's one of them called set input data, one of them called set input connection. The reason is way buried into the C++ structure. Just take my message as granted. ID here is a so-called VTK data object. So when we have a VTK data object, we use set input data. Geom instead here is not an object, it's an algorithm. It has a C++ class name of type VTK algorithm. So when we connect algorithms together, we use set input connection and get output port. And when we use data, we use this there. For the exercise of today, it's all done, so we don't have to really invest more time in it. Now let's look a little bit in more details in our source here of data. So that's our real data. How do we program that? Here's the example which I have prepared for you. There it is. We declare it as an object. It's a mesh. We have to give it its dimensions. So I have completely arbitrarily chosen a mesh of size 31 cube. You can change the exercise, make it any size you want. Image data is what we call a completely regular Cartesian grid. So it has regular spacing in all the directions. So it's enough to say what is the spacing between two points in the x, y, and z direction. This is exactly what this is. So I've selected 1 as a spacing. I give it the origin 0, 0, 0. I set the dimensions to be this. And this, in principle, actually, right there, yeah, is all you need to have on the screen a volume of size 31 cube. Now, we want to put some data on this volume. And there comes a little bit more NumPy magic for those of you beginners. Just take this as an example ready-made. Here's the data. We're going to create a one-dimensional array starting at minus 0.5, going all the way to 1, and of size 31. This will be for the x-axis. And for the y-axis, we do the same with different numbers. Z-axis, we do the same. Here we have 3 different arrays for the x, y, and z directions. We make a grid out of it. We take the x, y, z coordinates of this grid, and arbitrarily I said I want to calculate the square root of xc squared plus y, just to make up some data. This example is already made for you. You'll only have to execute it to demonstrate this. So this particular word, data, is a NumPy array. I need to attach it to the VTK object. It's pretty simple. Here's something I will use as a first line in all of my Python examples and code. I need to import the dataset adapter, and I call it DSA. Now, ID here is a VTK object. From VTK, I need to make it a NumPy object. So I wrap it like this. Image now is the same as this guy, except that it's a NumPy object. And on this NumPy object, I can say, take the point data and append the array data. The array data is what I have just evaluated here. And I give it a name, scalar. And here there's a special NumPy method called ravel, which takes a three-dimensional array and makes it just one long, contiguous 1D array. It's exactly what I said 15 minutes ago. All arrays are 1D contiguous in VTK. If we do this, oh, there's the example. So take here a two-dimensional array. If you ravel it, it becomes a 1D array. 1, 2, 3, 4, 5, 6. So we need to apply this. You learn it once and then you know it. There, that's all we have for this example. Yeah, we're done with it. So, image data, a Cartesian grid, we set the dimension, the spacing, the origin. Here, I've made up some data, but presumably this data will come from your simulation or from a file. You will import it as a NumPy array and then stuff it into the mesh. Last autumn, there were a number of blog articles by my friend Burke in the States. All of those have a link on my tutorials, and they're basically reproduced here. It's a second example. It's the same example, really. You recognize the source, the filter, the connection between the two. And here's something new, which we will not need to use very often. But let me explain. The pipeline execution is triggered by the renderer making an image. But if we don't make images and we would still like to execute the pipeline, we need to force the execution of the pipeline. In this particular case, we have a reduced example where we're not making any images. We're simply creating the data and evaluating it. So to force this particular update, well, it's called exactly that. It's called update. Let me rephrase that with an image. There. If we want to execute only up to here, we need to force the update of the filter. That's exactly what this command is. There. With the wrapping to take VTK object and transform them into NumPy arrays, sphere here in this particular example becomes a NumPy array. Point data is actually a dictionary. is a Python dictionary of all the different scalar and vector field associated with the mesh. What is a dictionary? Is there someone here who does not know what a dictionary is in Python? Okay, pretty simple actually. What is a dictionary? You open the page, you look up a word, and then you see the definition. Same thing here. This is called point data is a dictionary. It has keys, and those keys are a list of the words in the dictionary. So from A to Z. In this particular case, I only have 2 words in my dictionary. One of them is called normals. It's a string. The other one is called elevation. If I now take the string, the key, and index and use it to look up into the dictionary, this is exactly this, I get my NumPy array. So the Python, so point data is a dictionary indexed by the names of the scalar fields and the vector fields. All right? If I take the previous example, which I had called momentum, if I say my object point data string momentum, it will give me the array of momentum data. There. Now, they're NumPy arrays, so the things we've learned a few minutes ago, they're useful. We'll be able to tell the size of the array. So here's the example. Size will be 50. The shape of the array will be 50, comma. So it's a 1D array. And then we'll be able to, for example, take the first 5 elements of the array. 1, 2, 3. Here are the first 5 values of the array. And by the way, they are of type floats. But we can do a lot more using the same pipeline. We can use the indexing we learned about. So start, end, and step. Nothing fancy here. What about this? This now becomes really powerful. We take the name of the array and we say less than 70. And the response is, the return value is an array of Boolean values. For every scalar field in my NumPy array, if the scalar value is less than 70, I get true or I get false. In visualization, in many packages of visualization, we talk about queries. What is a query? An engineer wants to see all the data points where the pressure in whatever is building, the pressure is less than a particular threshold, or the velocity is greater than a particular threshold, except there. Those queries now are trivial to program using NumPy. This is the syntax. Name of the array, less than 70. We get true, false, true, false. Very good. Here's the gradient I talked about earlier. Shape, etc. Those we've seen already, but there's more. We can take now this as a query because it's a list of true, false, false, true, etc. We use this to index into the array itself, and here, as a return value, we have exactly all the numerical values in the array which are less than our threshold. So that's one query. Another one is the function where, which returns the indices where a particular condition is true. So if I take another condition here, NumPy array less than 40, give me the indices in the array where that condition is true. Those are the two indices. So we now have something that is a lot more than just a visual environment to do visualization. Take a package like ParaView. It's all point and click, mouse driven. You build your pipeline, but you'd like to do more. You'd like to do queries. You'd like to really go into your data to do to search for particular patterns, etc., etc. This is where all the power of NumPy comes in. So far, yeah, I've mostly concentrated on per tuple information, but there's also algorithms. Algorithms such as gradient, which I've mentioned, and I guess the example here is just about gradient. So this would be the syntax: calculate the gradient of RT data, assuming RT data is a scalar field. Okay? Now, if RT data 2 is a scalar field associated with an unstructured mesh, exactly the same syntax, and that's the great thing about this interface, the exact same syntax will give you the result, the correct result. All right, we're ready to put that into practice. So here's what we'll do. This example here is all set, ready for you to run. There's one for image data. There's one for rectilinear grid. So rectilinear grid is also regular, but it has a different spacing in the X and Y and Z direction. Typically, those grids I see are used in climatology, for example, where in the Z direction, we actually, no, let me take a different example. There might be latitude and longitude resolution which are different. So this would be a case for a rectilinear grid. In the case where we have a three-dimensional grid which sits on top of the topography, so it follows the terrain, this is yet another name. This is what we call a structured grid. In that particular case, the coordinates of the X, Y, Z points everywhere through the domain have to be given explicitly. It remains a structured grid, which means it can be indexed by ijk, but the coordinates are explicit. So I have an example called imagedata.py. I have an example called rectilinear grid.py, and another one called structured grid.py. So I'm going to first demonstrate how to do it, and then I hope you can replicate it. And to replicate the example, you'll have to do this. SSH to date. I would prefer you do this. You copy course, the bash RC to your own bash. This is my ID here. So I've added a couple of things which are nice. You'll need to create a VNC password. So just type the command VNC password. Decide on a password for yourself. Make it easy. Remember it. Write it down on a piece of paper. It's just for today and tomorrow. And exit ELA. Then we will permission. It's not readable. Okay, we'll fix that. I'll fix it right away. If I remember my password, that is VTK.